Good evening, everyone. So no one joined today till now, but we'll wait for 1-2 minutes. And welcome to the discussion on biomass conversion and biorefinery course. And today we'll discuss about the content of week 4 as well as week 5. So we'll wait for 1 minute. If no one will come, then we can start the discussion. So I'm sharing my screen. Okay. So today's discussion is of biomass conversion and biorefinery course of 2 week content. Week 4, where we'll go through the some answer of the assignment of week 4, and we'll understand the content of week 5, which will be helpful for you to solving the assignment. Tomorrow is the last day for submitting the assignment of week 5. So week 4 is all about biomass pre-treatment, which we last lecture we have gone through the basics of the biomass pre-treatment and some with respect to the assignment solving, and we covered many topics in it. And the week 5 content is physical and thermal conversion processes. In this today we will go through the some details about it. So if you talk about the professor's notes, then you have to refer the note from lecture number 10 to lecture number 15 for both week, for 10 to 13 for the week 4, 10, 11, 12 for the week 4, and 13, 14, 15 is for the week 5. So I am giving my introduction, as many of you many doubts they are asking after the class also. So my name is Bhavik Mahant. I am Prime Minister Research Fellow or a PhD student in the Chemical Engineering Department at IIT Madras. You can note down my mail ID as well as mobile number in case of you want to contact me regarding any doubts in the assignment or in general discussion if you want to do. So I'm again telling you that I am not associated with the professor directly. Last 2 weeks assignment has some discrepancies in the answers. I wrote a email to the professor, but I didn't get any reply till now. So, and I am a separate member of the NPTEL, where I just need to take the lectures on the particular subject, and so I'm not the course TA also. Okay, so we'll start with the week 4 biomass pre-treatment. Here we are solving the assignments problem for the week 4 currently. So this time we'll not go into the much more detailed discussion. We just follow the important point where the assignment questions were asked. So barriers in lignocellulosic biomass conversion. This is the first chapter, first few slides in this biomass pre-treatment, and they mentioned that lignocellulose biomass is available in many places, and it will be a much more good source raw material as a biomass, and we can convert many fuels chemicals out of it, and it has a potential to decrease the greenhouse gas emission, benefits to the rural economics, and promote energy security. And the main thing is these questions come from the assignment from this sentence: the composition of the lignocellulosic biomass varies with the biomass source and is affected by origin, age, climatic condition, harvesting and storage processes. Means it depends on the source as well as age, as well as with different kind of kinetic conditions, environmental factors, storage processes, and harvest. So as you can see, this is the question which is asked in the assignment. The composition of the lignocellulosic biomass varies with plant species, age, stage of growth. All of the above must be the answer. As we just see, the question is answer of the question is lie in that particular sentence. It affected by origin, age, climatic condition, harvesting, and storage processes. Now, chemical composition of the lignocellulosic biomass. So, these are the fundamental details we again and again discuss many of the times. In that, main concern of the different uh, composition, different uh, part of the biomass which has cellulose, lignin, and hemicellulose, as you can see here. So this is a different three part of the biomass, and mainly cellulose, hemicellulose we can broken down into the sugar monomers, sucrose, glucose, then glucose and fructose, and then we can go for the alcohol out of that, or maybe we can go for the biofuel, biogas, biochemicals, and uh, many other products. If you talk about the in detail, that mainly we have cellulose and hemicellulose. Cellulose is the polymeric chain of the glucose, and hemicellulose is the polymeric chain of the many components. Many pentoses are there, many hexoses are there. Then we have the not these two are the carbohydrates fractions into the biomass. So those questions, same question was asked into the assignment. And cellulose and hemicellulose, which are polysaccharides in the biomass, it can be easily converted to bioethanol, biobutanol, and other fermentation products. They can also be transferred into furan, both some chemical derivatives. And so the questions asked from this slide is the carbohydrate fractions of the lignocellulosic biomass is or are from which are this from this one. Protein, no, it's not carbohydrate section. Lignin is also not, but cellulose is the answer. So that's why the answer of this question is cellulose, as it is mentioned that carbohydrate fractions are cellulose as well as hemicellulose. So we have visited these slides in the previous lectures also. So cellulose is the made out of the long polymeric chain from the glucose monomer. Hemicellulose has these are a few examples. There are more compounds also possible. So pentose is like xylose and arabinose, and hexose is like mannose, galactose, and glucose combined together and make the hemicellulose. If we talk about the lignin, then lignin are the aromatic alcohols, coniferous alcohol, comara alcohol, and senapel alcohol. And as you can see from the biomass, if you take one biomass cell, so it looks like this, and you can directly see the extractives out in this. And if you again zoom it out little bit, and the green up and in this particular one part of the cell, then you will see that fibrous material like lignin and hemicellulose it's there. And if you zoom it out, you can clearly see the hemicellulose and cellulose out of it. So this is how we can separate out the different lignocellulose compound of the lignocellulosic biomass. Now, so there are some questions based on the cellulose. Cellulose is already covered, hemicellulose and lignin. So this is the again some small discussion of the hemicellulose. So hemicellulose is the second most abundant heterogeneously branched polymer. It's composed of pentoses like xylose and arabinose, and hexoses like glucose, D-mannose, and D-galactose. Some acetyl groups are also there. It's not only the glucose or sugar molecules are there. It has some uronic acid as well as acetyl groups. Everything is attached together, and it can form this hemicellulose. The question asked was hemicellulose in lignocellulosic biomass is composed of which are the following. The pentoses and hexoses are definitely there, and acetyl groups are there. We just see. So it is answer is all of the above. Okay. Now, so if we talk about the more detail of the hemicellulose, so this is all about the hemicellulose. Hemicellulose. So if you can see in the hemicellulose, These are the many fundamental monomers are there: acetic acid, glucose, mannose, galactose, xylose. Okay, so we are just solving the fourth assignment. We just go through the answers of the fourth assignment, and we will see the details for week 5 content, which will be helpful for the fifth assignments. So there we already covered 4 questions out of it, and now the questions based on the hemicellulose. So these are the different kind of monomers available present in the hemicellulose. These are not only pentoses, hexoses, but some uh, acids are there, as well as some aromatic compound is also present. So the questions ask from this sentence that composition of hemicellulose varies with the plant species. So there is a different kind of hemicellulose present in the softwood as well as in the hardwood. If we talk about the softwood hemicellulose components are the galactoglucosamine and arabinogluconoxide, glucuronoxylane. So these are the combination of arabinoglucuronide and xylane, and same like this. While if we talk about the hardwood, then it is a glucuronoxylane. So it's the main components, and all other things we already discussed in the last class. So which is the main component of the hemicellulose in hardwood? This was the questions. So answer is the glucuronoxylane is the answer, and it comes from the same sentence we just visited. And there was questions in from the lignin also. So lignin basically we cover multiple times, as there are 3 main compound: cellulose, hemicellulose, and the third one is the lignin. So lignin is not made out of any carbohydrate. So the previous 2 are made out of the carbohydrates, but lignin is the it's also polymer, but it has polyphenolic aromatics. Polyphenol means you can consider that aromatic alcohols are there. So there are many alcohol, so that's why it is also known as a phenol, because aromatic alcohol is phenol. So for, so it has many derivatives of phenol, and there if you talk about the some important monomer on this, the para-hydroxyphenyl guaiacyl serine gel. So these are the different kind of monomers is there in the lignin. And the question is which kind of linkage are in this, because it has a polymer. So some when the polymers come to when monomers come together, and between it will release some small compound like water and all, and they combine together and make a long chain polymers. So they link through beta O4 aryl ether bond. So we are not going to the much more detail of other things. The question is in lignin various monomer units are linked through which kind of bonds? So answer is beta O4 aryl ether bond. So it's a ether bond, and mainly whenever the alcohols are combined together, so in the form of polymer, as you can see here, alcohols molecules are there. If they combine and make the polymer, then you can easily see that H and OH will be come together, so you will get the H2O, and this combined with the help of O in between, so it will be converted into the ether only. So from this also you can consider the ether. Then you have to consider why 4 and 7. So for that mainly para monomers are there. So this is ortho, meta, and para. So when the other alcohol is combined from this part, then it is called as a para, and there is a 4 1 4 1 4 1 4 combinations is there. So that's a beta O4. Beta O7 never possible, because you are not, either you go from this side or that side in any aromatic. So this is a 1 2 3 4, or it's a 1 2 3 4. It will be never 7 is there. So this is how you can also work out with the answers. So in the same, some questions come from the different kind of pre-treatment. So last week we visited some methodology for the pre-treatments, which are the pre-treatments people are using, and why pre-treatment is useful. We can't go directly to the if we can directly go into reaction of the biomass conversion, then it will be a little bit difficult. So if we talk about the acid pre-treatment, so in the acid pre-treatment we we treat our biomass with the acid. There are concentrated as well as dilute acid we can use. They can so pre-treatment is basically we have hemicellulose, cellulose plus lignin. We are not going into much more detail. So we are doing the hydrolysis that will separate it out, hemicellulose, cellulose and lignin differently due in the presence of different chemical treatment or thermochemical treatment or the thermal treatments. So in that we are separated out. That is the main concern. And the question is, the main reaction during the acid treatments are, so it is mentioned, main reaction during the acid treatments are the hydrolysis of hemicellulose and condensation and precipitation of solubilized lignin. So first it is hydrolyze the hemicellulose. So you can take you will get the separated hemicellulose, and then if you condense, then condenses if you want to lignin out from that mixture, you have to condense that mixture, and then because when you give the acid treatment to somewhat temperature is high, then you have to reduce down the temperature, so vapors are condensed, and from that you will get the in the form of lignin, in the form of precipitation, because lignin gets solubilized into the whole acids. So this is answer, the hydrolysis of hemicellulose and condensation and precipitation of solubilized lignin. So you separate out the two compounds, so at the end you will get the cellulose also. So this is the main methodology in acid treatment. So organosol methods, where organic solvents we are using, or mixture of organic solvent or organic or aqueous solvents we are using, and in that we do the same hydrolysis process where the internal bonds of lignin and cellulose got broke, and you can easily separate out both of that thing from the cellulose. So the question asked was, the organosol treatment of the organocellulose material with the use of alcohol leads to. So as it is mentioned, so first thing is you can separate out the lignin can got removed, and at the same times so hemicellulose got solubilized. So that's why you can just refer to this sentence, solubilize hemicellulose and extract lignin. So this is the answer for this particular question. Now one question is come from the deep eutectic solvents are there. There is one separate technical process. In that we can use the we are doing the pre-treatment of biomass, and there are some physical processes, like if we apply the ultrasonic waves, microwaves, or different waves which can lead to breakdown of biomass structure, and you will get done final products. So this is how micro treatment is giving to the deep eutectic solvent. Eutectic solvents are the solvent which has two solvents are there, minimum two solvents got mixed. In that, one solvent has a hydrogen donor characteristic, other solvent has hydrogen acceptance characteristics. So in the presence of microwave, if you do the experiment, so this is how you can separate out the lignin. You can recover the lignin out of it, and other than that you can separate the cellulose and hemicellulose. So question was, microwave radiation in combination with DES pre-treatment enhances the efficiency of pre-treatment. So how it can enhances the efficiency of the pre-treatment? So why here it is mentioned that microwave radiation increase the molecular polarity of DES. As we mentioned that we have one compound of hydrogen donor and one is a hydrogen acceptor. So for donation of hydrogen, it is a oxidation process, and another is a reduction process. So if you want to enhance the oxidation and reduction process, if we can able to generate the molecular polarity. If a molecule is like null polarity, then it is different. If it has a polarity of one side of molecule has a positive charge, another is negative charge, so this will help to complete out this process. So that's why increasing the molecular polarity of DES is the answer for this one. already two solvents are mixed, it has a molecular difference in this, but by using microwave this characteristics is got enhanced and you can separate out the compound very easily. And there are combination of processes also in this particular different treatments. So in one of the processes acid and alcohol are combined together, so it's the acid alkalosis and alkaline extraction, it is given a name as like this. So in this particular table which is shown from the professor, there if you can't able to see into the presentation, please ignore it, but I will tell you what is the main content. So one is the acid treatment, what are the advantages and disadvantages, alkaline treatment, advantages and disadvantages, and sequential alkaline acid treatment if we are using, then what are the advantages and disadvantages. The question is the advantage associated with alkaline industrial pulping process are, so here the short processing time, simple processing steps, efficiency in cellulose pulp, and defined processing technology. So all are mentioned, so all are asked in the question, so this is the answer. And there is another process of pressurized hot water extraction. In that the question is asked is carried out in the temperature range of, so in this particular one slide of the thermal pretreatment process, it is mentioned that there are different processes with which has a different range of the temperature. So if you talk about the HTC hydrothermal conversion, then it is 180 to 250 degrees. If you talk about the pressurized hot water extraction, then it is 150 degrees centigrade to 180 centigrade. So this question is asked what is the temperature range. So temperature range is 150 to 180, that is the answer. So this is all about the week 4 content, which maybe you already got answers, and week 5 is maybe the tomorrow is the deadline for the week 5. So we'll not cover each and every topic of week 5, but we'll cover the all major topics and the questions asked from the all the major topics. So week 5 is the physical and thermal conversion processes. So basically we started with understanding the biomass. In the first chapter we understand the worldwide scenario. In the second chapter we understand the biomass, in what are the properties of biomass, where what is the source of the biomass, and what are the characteristics of the biomass. In the second and the third chapter we went to the biorefinery. So out of how we can utilize this biomass and how we'll get the products out of it. This is our third chapter. Then in the utilization of the biomass, the first step is the pre-treatment. We have to do the pre-treatment of the biomass in the form of, we can separate it out the hemicellulose, cellulose and lignin, and we can do the next phase of reactions or next phase of process on the individual compounds. So we'll get the range of products depending on to the properties. Now we did the pre-treatment also. Now it is the times to convert the biomass into the final products. So in that also, in this particular week we follow two main type major categories. One is the physical and thermal conversion processes. It's not like that in physical thermal we are not go through the reactions. So if we have physical means, you can increase the pressure, you can increase the temperature, you can reduce the same pressure and temperature, you can play with the volume and all the physical characteristics, density and all, you can play with it. And thermal conversion is mainly focuses on the temperature, how if you increase the temperature, high temperature. So physical is cover lot many things. If you directly do the mechanical processes where you crush the biomass, you reduce the size of the biomass and it will convert into some products, or it will convert into some intermediate products. So that is comes under physical. And thermal conversion is we are providing the temperatures and with pressure or without pressure upon depending on to the desired processes, desired product, desired process towards the product, and will get the products. So here it is not thing like that, the chemical reactions is not happening everywhere. If you are providing some thermal conversion is there, so chemical reactions definitely there. So there are some chemical reactions happening in the back end of the process, and you will get some products. So start with the discussion. The physical processes are employed to prepare biomass for use as a fuel or as a feedstock for a conversion process. So mainly physical processes are still one intermediate step where you use these physical processes, and at the end you will get the biomass into the form where it can use as a feedstock for the final conversion process from biomass to product. When the processes examined are dewatering. What are the physical processes we mainly covered in this particular discussion? Dewatering, so removal of water or removal of moisture. Drying is also moisture removal, but there is some slight difference in between. Size reduction, we are reducing the size, so it will increase the surface area. And separation, densification is there, so we increase the density of our biomass and we separate it out. So these are the things which are going to discuss in that. I attached some of the figures and data from the which are not there from in the professor's slide, so you will get to know some different kind of information rather than just I repeat all the things which you already maybe you watch already into the professor's discussion. So the type of the biomass, and there are questions on this thing also, that how much moisture percent it has. So water hyacinth, so there are some vegetables from the water. There are some aquatic biomass which come from the water. So water hyacinth, it has the highest amount of moisture percentage. Daily cattle manure, so we have the uh, cow dung and all, so it also has a high amount of moisture percent, like up to 80 to 80 90%. Rice straw, these are the agricultural waste. Food waste, this is the range. Corn stalk, wood bagasse, poplar, sawdust, switchgrass, these are different kind of things are there. So it will be helpful for you to understand which is the, this is not even to uh, in maybe in the final exam you will not they will not ask the questions like that you have to remember the moisture percentage, but this is for your understanding that the moisture percentage in the biomass is then it ranges from the 6.5% up to 95.3%. So depending on your process, you can't use any kind of biomass in any kind of process, so you need to understand the characteristics of the process and requirement of the process. So this is a dewatering and drying slides from the professor. So dewatering is the removal of all part of contained moisture from biomass. So dewatering is you will remove all kind of moistures, means whatever amount of moisture is present you will remove it. And drying is you will remove the moisture in the form of vapor. So you are providing the heat and the moisture is converted into vapor and it get removed. But after some time, if you can go to the mass transfer, so there are many long channels are there, if you know, inside the materials. So sometimes the moisture are there into the end of the channels, very deep in the channels, it will be not come out by the drying process. So drying is a process, but it is only remove the vapor in the form of moisture in the form of vapor, that's it. So then there are many kinds of drying is there. We already have visited maybe mechanical unit operations or different subjects that many kind of dryers are there. The process also, we can use open air solar drying, which is the lowest cost because we are using sun energy. Other than that, we can use some industrial dryer like spray dryer, fluidized bed dryer, rotary dryer, vacuum dryer, drum dryers, kind of dryers. And the key biomass property that should be obviously be examined in addition to conversion process requirements like moisture content of the fresh biomass. So it is more important to moisture content of the biomass, which will be define the final product. So that's why we have to understand that how much amount of moisture content is there. So if you talk about the drying in particular, so because dewatering may be not that much useful in it is a whole range of processes are available where we are dewater the final biomass, but drying is must needed. So drying a little amount of moisture is already we can able to reduce, you have to reduce, that is the main purpose. So the mechanism is there are several drying, we know that how this drying process are take place. So mainly it exposed to the low humidity air, heated air, and the final moisture content of the air biomass is usually in the 35-8% range or less. So if you use the drying, so this may be the questions or something, that how much what is the final moisture percentage after drying. So it is a 35-8% or less than that. So what are the disadvantages? This process is slow and it is a localized. Like if you put the drying so much, if you just this is a plate there. If you put the dryers in this, so it is a localized process. It is not like that it is got dried, so you will get this one is also dried. So once and all, it exposed to the hot air and it can got dry. If you go for the sunlight, open sunlight there, then you have to go for the labor, manpower is required, and these are the main points. For forage crops have traditionally been partially dried in open air to the moisture level, so they can remove from the field and store without significant deterioration or loss of the nutrient value. This is then also facilitates densification of hay by baling. So we'll go through the densification in the next slides. So if you just understand, then these are the some of the dryers. So first is a rotary drum dryer. It is moving in the axis, and hot air is you in this particular silent tube kind of sometimes arrangement as there. The steam tubes are there, and your material feed material is going from here to here in the conveyor, so you will get at the end final dry product. Then this is a flash dryer, so you enter there, and due to this particular shape, the flash reaction has happened. So suddenly pressure can got drop, and as well as volume velocity got increase. So it can water can got out easily. And then it is a fluidized bed dryer. We are putting the hot air and it is converted into fluidized bed. And then ring dryer. This is a new dryer, new kind of dryer. So in that one ring is there. So air is coming from here. Your biomass is here. It will take it out, and what is the water is there, it will be go what your product is there, it will go with this into the separator, and the weight product, which is a high density heavy product, it will again go into the ring. Next phase of air will come, it will the similar process, and it will at the end you will get the final dry product. Spray dryer. So spray dryer, we all know that it is in that it is converted into slurry, feed into slurry, and then it got sprayed, and from down you have the air, and then the final product is going to cyclone separator. These are the some revision of some kind of drying if you want to go for the specific biomass drying. So these are the major industrial dryer which are using into the biomass drying. So these are some slides also, so maybe it's not visible to you, but I next time onwards I will not use the slides, I will use the content. Because why I am using the slides, because there are some questions from these slides directly asked into the assignments, so that's why I use the slides, but next time I will use the content only. So dry biomass burns at high temperature. If you have the dry biomass, then you have to take care of the drying process. It can be burns at a very high temperature. If you go for high temperature, it will higher thermal efficiency than wet biomass. So means after drying, whatever the dry biomass you have to go for the high temperature, but it has a very high efficiency. There are two contradiction thing. So your process will be the conversion process have a high temperature. Flame temperatures of green wood for 58% moisture and dry wood in conventional combustor that supply boiler heat are 980 degrees centigrade, and these are the some range. If you have the flame, so what is the flame temperature? It is mentioned the flame temperature. Flame temperature is the temperature, the amount of heat necessary to evaporate the moisture content in the wood. The lower moisture content, the lower amount of energy needed to remove the water, in the higher the energy of the higher the boiler efficiency. So it is the amount of heat necessary. So how much amount of heat is required to evaporate the moisture content, and if you have lower the moisture content, the lower amount of energy needed to remove the water, and it has a higher boiler efficiency. with the exception of suspension firing unit, for which the moisture content of the fuel is usually the 28% range, and the maximum is 55 to 65%. So this is all about drying. So combustion of biomass containing 65-8% is in the conventional system can result in lowering the adiabatic flame temperature to the point where self-sustained combustion does not occur. So these are some information how we can take care. So if we have more than 65-8% moisture and we use the conventional system, or you can say the furnace, so what happen? It can result in lowering the adiabatic flame temperature. So what is the adiabatic flame temperature? Adiabatic flame temperature is the temperature energy required to convert your water liquid product which is present into the vapor. So if you have more water, then this obviously, suppose you understand 10% waters are there. So suppose this adiabatic flame temperature is because more amount of dry material is there. So for removing the very small amount of water, we have to reach the temperature up to, let's say, 90 degrees centigrade. But if you have 60% or 65% water, means so much water is there, so it is our heat is directly exposed to the water, so it start getting you don't go for that let's say 190 degrees centigrade, otherwise you will go understand that why this vapor is converted before 100 degree and all. So it's a 190 degree. If it 10% 60-65%, so it may be in 120 degrees centigrade also your water got converted into vapor. So this is the adiabatic flame temperature got reduced. Many of the large-scale biomass combustion system for producing heat, hot water, steam, except biomass fuels containing relatively large amount of moisture and are operating without much apparent concerns. So that is a main concern. People in conventional processes, they are not understanding that if you have more amount of water, if you have moisture content, then it has basically difficult for us to treat into the conversion processes. So on an average 58% moisture are currently used in the biomass fuel power plants, and these are the some amount of drying. So why drying is important? So I have one video, so you will not get maybe sound or something, but you will get sound also, but main thing is sound is not required. Everything is written as a subtitle, no, as a processes. It is written onto the screen that what process is going on currently. So it will be helpful for understanding how actually these drying systems are look like, for particularly if we talk about the biomass. So I found one video. So this is actual equipment, actual dryer, and how drying take place. They explain into the whole thing step by step. So just take a look. So this is a dryer which has a 8 tons per hour biomass drying system. So it can able to dry 8 ton of biomass in an 1 hour. So this is the horizontal part is dryer part, and this other part is, I think, cyclone separator. So just see. So this is a weight biomass. As you can see, it has a half each weight biomass chips. They come and it is put into here. You can see it is a very high moisture content is there. Then all the weight biomass is by using sorry, maybe I touched to the screen. I don't have to touch. So it is going into the some feeder. So directly it will directly not reach up to the dryer by using to the feeder. Feeder means conveyor belt or some different kind of belt where solid material can go transported from one place to another. So this is a conveyor. Now after this feeder, the actual amount of continuous amount of biomass get transported to the feed hopper. This is a feed hopper in which this biomass is going to feed, and it is directly connected to the dryer. This is the drum, horizontal drum. So it has I guess steam for drying. So it is a 50 feet long and 8 feet in diameter. So particularly 8 ton per hour capacity. This is that requirement design. So once it will go inside, they will supply the steam inside it. And why it is rotating? So once it is rotating, so each and every part of the biomass is exposed to the uh, hot air or steam, and then it can easily dry. After that, once the product is got dried, it comes with the cyclone separator, because after drying you need to remove some unnecessary unwanted. So you can see there is one, it's how much dimensions are there. And this is from the discharge conveyor. So how you say how which color of the biomass was there, it is a very sticky and black color, but at the end you will find it's a kind of wood strips or agriculture waste. So it got fed into the bag, and you can go for the next processes. So this kind of industrial biomass actually people are using in terms of whole commercial level biomass conversion processes. And this is that one part is the final biomass, and this is all weight material, and one extra material it is present. So this is a US based company. So there are many, you can, if you just want have to curiosity to understand all these things, you have to just write the whatever you want to learn into the YouTube. You will see the many kind of videos are there. So we all of us discuss all about the drying, and we just saw the videos also. Now what are the other important processes? Another is the size reduction. So why size reduction is required? So as you can see, if you process it into the bigger size, suppose 1 foot by 1 feet, and then it has very less surface area. If you convert it into the 1 centimeter by 1 centimeter, then there are so many parts are there, so many surface area got increased, and that will be helpful to process this biomass in an efficient manner. So again, some professors talk that size reduction, if you talk about fundamental of size reduction, then the reduction is physical size often required. Why it is required? Because first it is mentioned it is required, and it can be, this biomass can be converted into the pellets, cubes, briquettes, or conversion, different kind of small shapes. Smaller particles and pieces of biomass reduce its storage volume, facilitate handling of the material into the solid state, and transport of the material as a slurry. So if you have the bigger particles, then it is very little bit difficult to transport it in the whole solid form. But if you have small particle, then it can easily transport by using the pneumatic transporter, or if you can convert it into the slurry. The size of the pieces or particles can be critical when drying is used, because exposed surface area. So if you have the bigger size, then obviously drying is not that much effective. And there are few exceptions where size reduction is not needed. Sometimes size reduction is not required, but these processes are not that much in modern day we are using. Conventionally people are using whole tree burning and all. The size reduction is not required, but country people are not using. So these are the maybe some questions come from the particular dry shredders, which is a size reduction equipment. So it is a commercial use for reducing the size of biomass. Okay, so this is the equipment. So if you want to see in the better picture, so this is how it is actually and it looks like. So if you put in that if you put the whole big chunks of blocks of wood, then also you will get the final product like this. If you put this kind of briquettes also, then also it can convert into this. If you want this kind of product, this kind, any range of product you can convert by using this kind of shredders. So it is mainly it is working from the by using the mechanical device. So motors and all that all things are there. So you have to think about the energy conversion, energy requirement. Someone is there? Okay, so we are discussing the week 5 content. We have visited the week 4 content. Some assignment questions answer we solved it, and now we are we jump into the week 5 content discussions, and what are the important thing which is useful for you to understanding purpose, and at the same time which will be helpful for you to solve the assignment questions. So if you can't able to see that screenshot of professor slides, so next time onwards I will take the content, and we are discussing, we just saw the video of drying process. Now we are shifting to the size reduction. So size reduction is why it needed, because we can increase the surface area of the size, and if you have the bigger size, then it's very difficult to transport from one place to another, and drying is also not that much effective. So that's why in this particular, it's like if you go to the mechanical unit operation, there's a hammer mill. So it's a similar kind of structure. In this hammers are there. So hammers in the sense any kind of rotating metal part, which when this big logs of woods or big logs of biomass come in cross contact into that particular hammers, it get crushed. Okay. So commonly it is used for the municipal sewage waste, where we are reducing it and before the separation of RDF. So when we are using the municipal sewage waste, so you will get the refuse derived fuels. So we'll see into the future slides. So RDF, you want to means municipal sewage waste. If you remove some compound which can directly use as a, after some treatment, as a fuel, so it is known as a refuse derived fuel, RDF. Now densification, there is, after size reduction, there is also another process where densification is good. So as the name suggests, density means it comes from the density or dense properties of dense you can consider density. And fication, so how can we increase the density? The simple definition of densification is, how can we densify the material? Densify in the sense, how can we improve the density of the material? Now why and density improvement is needed? So first and foremost thing, if we have the biomass, we have the small wood, hardwood, small any kind of agriculture waste or all. So if we have the very light density material, then it's little bit difficult in the for the handling of the biomass, and at the same time it is little bit difficult to go for the treatment. Like if you go for the thermochemical treatment or thermal treatment, then if you have dense material, then it's easily the heat got conducted from with the help of conduction, heat got travel from one part to the all other the biomass part. But if you have so much void spaces in between, you can consider that if you have very void spaces are there, so heat got wasted also. So energy conversion is also not taking place, and energy conservation is also not taking place. So densification, so baling is a process mainly people are using for the straws and different kind of fibrous biomass is there. So in our other agriculture crops are there, so because it has very low density. So baling, what is a baling? So baling is we press it in such a way so it can increase that density. So they are giving the range that bale straw. Straw means whatever the agriculture waste, we can give the name as a straws, or so the if you provide the baling which can reduce the the other thing is, if you have the light density material, then it requires a large amount of storage. If you just densify it, then it will reduce the storage space, and it reduce due to storage space, it reduces the transportation cost also. And it is mentioned that bale straw has a density of 70 to 90 kg per meter cube at 10 to 15 weight% moisture content, whereas the bulk density of pile straw is about 5 to 15% of this density range. So as you can see that density is more 70 90 weight%. If you don't do it, and then it has a density around 10 15 up to 20 kg per meter cube. So increase the density when straws are compressed to form pellets. Now we just visited in some slide that you have to convert your biomass into the pellets, briquettes, small cubes and all. So how can you convert it? So for the pelletization is also process of densification. So you have the biomass and you can press it into the form of small pellets and all. So then the density can be increased from 350 to 1200 kilogram per meter cube, while dry wood has a density of 600 to 700 kilogram meter cube and bulk density about 350 to 450 kilogram meter cube. While you convert it into the briquettes, these are some important information. So 700 to 800 kilogram meter cube, and up to it can go for the 350 to 1400. So how can we do that? If you just understand in the small simple cartoon, then this is the, it's a piston kind of thing. Oh, sorry, I selected the, wait, okay. So this is our biomass. You can see there are so much void spaces are there, and this is a piston kind of thing. You applied the force above it, and then it got filling this void spaces and reduce its volume. And if you apply the force up to the some limit, or it is a predefined up to predefined force value, then you will get this particle deformation is also there. So if you have particle in the form of round shape or elliptical shape, it convert into the square, and then it will convert into the irregular shape, and then it is a, if you can take it out, then you have this kind of cube, not cube, it's a kind of rectangles material is there. So this you can convert it into the cubes, briquettes. This is actually called briquettes. And so why it is agglomeration? You can also tell this densification as a agglomeration. Agglomeration is when the different particles are come together and agglomerate. Agglomerate is a combine together and make a bigger structure. When you have small particle come together and make the bigger structure. So it can be like, if you can see it's a very small particle, you can agglomerate by using the liquid, and then it can convert to granular product. This is little bit different from the densification. It is not into the professor's topic, but I just add it. Not always people are using densification. Sometimes they are using this agglomeration process also. So in that also apply forces and this energy, fluidity and temperature, everything needs to convert into process parameter. Material power properties. So powders, if you have increase this, consider the how we can useful for these agglomeration processes. So you have to think when you are developing the agglomeration process for the powders, what are the safe surface area, roughness. If you use some binder, so this liquid is known as a binder, which will be bind the material. Then transformation is through the weighting, mixing, reaction, any kind of process is there. And for what at the end, what you are get as a final product, what are the attributes, what are the characteristics. Particle size, high small particle size, high surface area, flowability is good, yield stress is good. Ultimately you can handle this biomass in a very good manner. Okay, I just want to drink water. Wait. Okay, so we go to the next slide. Then after densification, separation is also important. So what is the separation and how it's separation? So it is desirable to physically separate potential biomass feedstock into two or more components of different application. So as we know, as we saw in the last class, even in the today discussion also, that hemicellulose has a different range of product. Mainly cellulose and hemicellulose has alcohol and biofuels. If you go for the lignin, then it will have some chemical polymer as a products. So you can convert this whole biomass feedstocks into the different components, different separate sections, where the more components are predominantly present, and you will get the products accordingly. So the subject is quite broad. So it depends on the which kind of biomass are using, because there are many kind of biomass. The separation is not like you have to separate this in particular manner or particular process. So it depends on your types of biomass, source of biomass, and what the final product you want to achieve, and depends on the process also. So if you want to go for example, then separation of agriculture biomass into foodstuffs and residues. that may serve as a fuel or as a raw material for the fuel manufacture. So if you agriculture biomass, then some food parts is there, you can convert into the one part, and another is the residues of that part. So this can be one example. So major seed separation process is useful when we are using the municipal waste, solid waste, MSW, as our biomass. If you have MSW, as I told, that it has a mixture of organic and inorganic materials, so efficient separation and economical recovery of RDF is be there. So RDF is a refuse derived fuel which can convert into the fuel. So which are some components that can be, you can convert the product into the fuels. So so this is a challenge. So how to get separate the inorganic material, organic material, and RDF, and how can we recover the RDF? So that's why the separation needs to be take place when MSW we have treated as a biomass. And who started the first comprehensive recovery plans? Then name is that county from Florida. Florida is in the US. So the first major plant of this separation of municipal solid waste was developed into the US. So which is useful the full scale recover recyclable RDF, yeah. And the plant was designed to produce approximately 3,000 ton of per day, but it can also process up to 4,000 or 5,000 ton per day depending on to the biomass which you are using. So and the recovery one, there is another plant. This is also built in the US only. So the name of the plant is Recovery One, and it is located in the New Orleans, Louisiana. Louisiana state. There is one state in the US which is Louisiana. Florida is also one state. So which has a capacity of 590 ton per day. So the earlier one has a very high capacity. So but this is maybe the compact unit and the smaller scale unit. The waste was delivered and unloaded at one of the two receiving pit conveyors and transported by conveyors to the first separation unit, a 13.7 meter long by 3 meter diameter. It's a like trommel kind of structure. We see the in the dryer also, it is like horizontal. This is a trommel, rotating trommel is there, and it has some circular holes and all. So all this depending on to the your product, your biomass, it gets separated. Now this is the important slide because many in the urban many countries focus on the urban waste, urban municipal solid waste to convert into the energy. If we talk about the countries like India, Brazil, so we have agriculture waste in the huge amount, even in the South America also. If you talk about Australia, but not all the countries. If you talk about the Europe, you talk about the Japan and all, then all countries doesn't have this kind of agriculture sector very well defined or very well developed the agriculture sector. So they don't have the biomass come from the agriculture, and at the same time they don't have the biomass from the different source of the vegetables or marine source and all. So what is the never ending source of all the state, all different kind of countries or different kind of scenarios is the municipal solid waste, because all countries as the big cities are there, and tons and tons of solid waste is got generated every day in India also. So every country has this municipal solid waste. So you can see that most of the energy development, technology development plays into the biomass sector or the biomass conversion. It is in the sector of the municipal solid waste. So there are Netherlands, Norway, Finland. These are the three important countries who drive the research, and as well as US also, because they have the large amount of municipal solid waste. Now if you want to energy out of it, say there are three main processes which we can use. One is a land mining. So land mining is a conventional, little bit conventional process where you use the solid waste and into landfill it. So there are two ways. You can directly landfill without any gas recovery. So whatever the gas will be generated, it will go into the environment, or it will be spread it out into the landfill area. But if another is a landfill with gas recovery. So obviously you landfill in the sense you you make some big huge structures where you put all of your solid waste, and above it you can use some um, different kind of materials, actually bentonite clay they are using. So you put your solid waste and above it you put it like this to whatever the solid waste is there, so it will got stored inside that huge structures. But once the solid waste organic materials are there, it get go into the store into the clay and all. So it is releasing the gas, which gas? Mainly methane gas, because that biological degradation is taking place, so gas is be removed. So if you can recover the gas will be useful as an energy source. So that is methane mainly. Another is a biological conversion, where you took this municipal solid waste, and there are mainly two things. One, you can composting. You are using some microorganisms, bacteria, which convert this biomass, this MSW, into the some compost. Compost means the fertilizer, which you can use into the agriculture sector. Another is anaerobic digestion. If you are not providing air, and if you are using some kind of bacteria, then it will be converted into the biogas. Maybe gobar gas is a common term which in India we are using. So this is also same process. So it will convert into biogas, which is mainly predominantly methane. It is covered with energy. And then if you talk about the thermal conversion, the thermal conversion is so mainly some some MSW is there, which cannot be easily converted, which cannot be treated. So that in that process, that time we are using this kind of processes, which is the thermal conversion, which is provide the high temperature. Incineration, so we are providing the high amount of heat, so it will convert it into the steam, and it can be used for the heat and power. Same refuse derived fuel we have, it can be converted into the heat and power, heat or power. Pyrolysis can be done, where we are providing without in the presence of oxygen, we are providing the very high temperature, it can convert into the some products like charcoal gas and oil. Gasification, again you provide a high temperature, so solid is got gasified, and you can use it in the synthetic gases. So this is how it looks like if you have municipal solid waste, and this is the overall process. So first of all, this is from a dustbin need to go into the processing unit. So in the processing unit, mainly this is a thermochemical process or thermal conversion you can say. So you will get many more products out of it. So mainly these thermal processes are much more well known or popular you can say. So this is the whole furnace is there. So we are putting your biomass, and we are providing very high temperature. So and then after that you convert it into the steam. This is one of the approach, it's not a only approach, it is one of the approach. And this convert to steam, and steam can be used by the as a boiler unit, and you can generate the power. So by using turbine and all, you will generate the powers, as well as you will get some you are utilize this power product into the after this hot stream. If you once you converted into the boiler, your hot steam is be used, the steam got temperature got reduced, you can use it into the cooler and something. So that is also two important utilization. After that, there is a spray dryer bag house is there. So at the end, in this what is the spray dryer? So whatever the dust particle and other particles are there, so which will be dry here, and then unnecessary particle and which is not useful for environment, we can take it out, and some water vapor and carbon dioxide we can remove it from here. And other than that, you can at then whatever the final product which will get you can't use, that will be go into the either landfill, either go into the aggregate material, or some metals are there. So this is the overall processing which many countries are following. So thermal conversion products. So what are the products? So in this some slides professor discussed different kind of products. So mainly this food waste, if we talk about food waste or the MSW, so it can be converted as a residential waste, institutional waste, commercial waste, or industrial waste. So commercial waste, agriculture waste or supermarket waste, and industrial waste with the food processing industry waste can also be classified as a pre-consumption food waste. So agriculture, supermarket, or you can see that food industry or some processing end, so it's pre-consumption. Whereas residential and institutional, so some if you have cafeteria, hotels, restaurants, or home, so whatever waste are generated, it is a post consumption, which is a consume first from the human being, and then you will get the waste. That is the post consumption. And pre-consumption is that it is not even consumed by the human. The mixed food waste sources from post-consumer subgroups are characterized by high moisture content, high organic content, and high salt-rich nutrition, which are very valuable. So we can mix the food waste, and then we can play with the different characteristics of the waste, and that will be helpful for our process. Then thermal conversion, if you take the unprepared food, it go for the food preparation. If we add water, water addition removal is taking place, and some amount of food in the during the preparation, it can spoil or unreserved some excess food is can be go for the in the go into the pre-consumer waste. But after prepared food, it will go into the consumer food, and whatever the excess waste or something is there, it is known as a post-consumer waste. So maybe some questions are there in assignment, you can give the answer. So if you talk about the food waste in general, so food waste is that same, which is a major part of the MSW. We can go for the physiochemical processes, where we are using the physical parameters changes in the presence of chemical. And there is a thermochemical process, chemical reaction takes place in the presence of temperature. And biological, thermochemical is the main process. Many technological development was done in that. It is the incineration combustion, where you will get heat electricity, and the byproduct is the S. We just saw this all things, but I just revise it. Pyrolysis is the main product, char, bio oil, and syngas. Byproduct is charcoal. Gasification, if we are using the char, bio oil, and syngas, and byproduct is S. Hydrothermal carbonization, hydrothermal liquefaction, many processes are there. You will get the hydrochar, and the byproducts are the crude oil, processed water. So that's why food waste is also MSW is much more important. Now we talk about the gasification. So gasification is name suggests the solid product we can solid biomass we can convert it into the gas form or gasify it. Mainly coal gasification is the very well-known term. If you don't maybe not know the gasification, then if you convert coal into the gasification form and use as a different for the different application, like directly some chemical production, or you can use it in the power generation also. So that is a coal gasification. Here the gasification of biomass mainly partial, it is a partial oxidation process. So we convert the biomass into the mixture of carbon monoxide and hydrogen, as this is a syngas, or this gas is much more important for many more processes, power generation and all. So if you are to go for the total oxidation, then CO can also convert into CO2. So this is not required. So we require a mixture of CO and H2. That's why we are going for the partial oxidation process. And if you want to achieve this partial oxidation, the temperature is more than 700 degrees centigrade without getting combustion. So combustion is a combustion process where we are getting the CO2 and H2. So CO2 and H2 is not required. So we have to think that the combustion process does not take place. And control amount of oxygen steam, whatever amount of steam and oxygen we are giving, it is a not excess. If you want to go for the CO2 then on H2O, then you have to provide the excess amount of oxygen, then CO can convert into CO2. First CO can got product produced, and then it will convert into CO2, and H2 is H2O. But if you have control amount of oxygen or steam, then it will remain CO and H2. So gasification typically uses 25 to 40% of the theoretical oxidant, pure oxygen air, and generate enough heat to gasify the remaining unoxidized fuel. So whatever the actual, let's say 100 moles of hydrogen, 100 moles of oxygen required, you just supply 25 moles or 40 moles, then it will be converted into the CO and H2, not into CO2. So gasification generates lower amounts of some pollutants. So as we are not providing more oxygen, so all the pollutants, sulfur, nitrogen is there, it can also convert into very less amount. SOx and NOx will be less amount in comparison to combustion. If you go for the combustion, then this process, this byproducts, or mainly the environment polluters, are in the very high amount. So in gasification, so if we talk about the different feedstocks of coal, biomass, petroleum coke, revised waste, so this is a general. Mainly we talk about the biomass. So how it is, if we convert, if we use as a solid feedstock and put it into the gasifier, this gasification process taking place in whatever the equipment which we give the name as a gasifier. Okay, so first what you are doing, you are providing the heat here. How you can providing the steam? So you are providing the steam from steam power plant with steam turbine. You are providing the steam, and it is going down. It is fading from the downside. So whatever the solid is there, it will convert into gaseous product, and then gaseous product is go into the first in the separators, where you separate out the particles. First solid particles still present, you can separate out, and then whatever the gas is there, you can go into the another separation unit where sulfur and sulfuric acid will be removed. Whatever sulfur amount is there, it will get removed, and then you will get the COH2 syngas, which will be useful for the fuels as well as chemicals. And you can separate it out, the hydrogen out of it. A hydrogen can be used as a transportation fuels in the vehicle, and you can use into the fuel cells, where you will get the electricity, and then it will be used as a electric power. And the syngas, the another thing, whatever the syngas which we are converting for the fuels and chemical, which we can again use into the combustion process, or in the boiler or steam turbine, where you can it will be helpful for providing some, because it has oxygen in it, so you can use the oxygen again for the recycling of the same. Oxygen is required for this gasification, 40%, up to 40% oxygen. So it will come from the air as well as this fuel, this syngas reaction. And the other thing is, you can again, after turbine, you can use the same syngas for the electric power generation also, as well as whatever the carbon dioxide is generated in this process, you can have to sequester. As we discussed multiple times, that carbon dioxide means net zero is the target of all over the world. In India took the target of 2070. So whatever the amount of carbon dioxide is generated now, we have to go for the sequestration or storage of carbon dioxide, utilization of carbon dioxide in some way, that in the future will not emit much amount of carbon dioxide. So that's why CO2 sequestration is useful. So this is a whole process which one can follow in order to do the gasification process. Now what professor suggested, so in the gasification mainly many reactions are taking place, and if we use that all the reactions into some particular groups. So in the first process, which is known as the first reaction, is the dehydration or drying process. It's not an individual reaction. There are multiple reactions are taking place at one time. So first reaction is the dehydration or drying process. Once the temperature of the gasifier reach up to 100 degrees centigrade, then the drying process is take place. So whatever the moisture is there is converted into the whatever steam is get the moisture out of it, and moisture converted into a vapor. The second step is the pyrolysis process, or pyrolysis process has another name, devolarization process, that occurs around 200 to 300 degrees centigrade. So whatever the volatility product are there, vapors, volatile materials are there, it can be go out. So you will get the solid charcoal. Solid product is converted into the char. It is known as a char. It is basically coke, which is a charcoal, or which can be used for the energy. So the process depends on the properties of biomass. Then the third process is the combustion reaction. So the char, whatever the char which you got here, charcoal, it's short from the char, is got here, that can be converted into the carbon dioxide, carbon monoxide, and it can provide the heat for the gasification reaction. After this combustion process, it can major part of the combustion process is CO2, but our main focus is on the gasification process. So we are providing the less amount of oxygen. So that's why this after combustion, little amount of combustion, you will get the gasification process, where your char is reacted with the steam and carbon dioxide to produce carbon monoxide and hydrogen, CO and H2, which is our main product. So the reversible gas phase water gas shift reaction reaches the equilibrium very fast at high temperature, and at the end water gas shift reaction. So water gas shift reaction is nothing but CO plus H2, sorry, CO plus H2 is go into the H2O CO2. Okay, so here 2H2O, 2CO. So you have, so here it's not required. Anyway, you can balance it out, but it's like that. Carbon monoxide, hydrogen is reacted in water, and CO2 will be get. It's the water gas shift reaction. So it will be got equilibrium, attain the equilibrium. Okay, so we just now these are the reactions. So gasification with oxygen. So coal, oxygen and steam is there. So first we get the C plus half O2 gives CO. It's all the reversible. CO can also convert into C plus half O2. Combustion with oxygen. This is the gasification. This is a require. This is desired reaction. Then combustion is converted into CO2. Gasification and carbon dioxide. If you have first combustion, then if you go to this reaction, C plus CO2 can again convert to CO. Gasification with steam, we have the water H2O, then again convert in C called carbon, and it will convert to CO plus H2. Hydrogen, if it is gasified, you will get a methane. Water gas, if CO plus H2O gives H2 plus CO2, you don't need to put a 2 in there. So methanation process is also there. If you have CO plus 3H2, more amount of hydrogen is there, then convert into methane and water. So gasified gas composition, you will get so many products. Mainly we will see the hydrogen and CO. Hydrogen is around 25-30 volume percent, CO is 30 to 60 volume percent. These are the main products. And other, because you control on your reaction conditions as well as oxygen amount, that's why majorly you will get H2 and CO, and the other products subsequently in some other volume percentage. So again it is the same explanation. So what are the temperature? If your first is biomass is there, it will go through the drying process. The water is drying off at 100 to 150 degrees centigrade. The another is a pyrolysis process. The second process is without the presence of air, you do the pyrolysis process in the 200 to 500 degrees centigrade. Then it converted into the char or charcoal, and you will get H2O, air, tear gases. Then the combustion and cracking processes take place. Combustion, cracking, or combustion and gasification processes take place, and you will go to H2O plus CO cracked tar. Cracking in the sense, so whatever charcoal is there, it will convert into or gases are there, it can crack into the final product. So it is at 800 to 100 degrees centigrade, and then reduction process is there around 650 to 900 degrees centigrade. So you will get the producer gas H2 plus CO and char S, and then char S, which will be also maybe used for in some products. So this is these are the sites are not explained by the professor. I download it, but if you want to go into the detail and all, you can visit and read or watch the professor's videos or professor notes. Now we understand why gasification require passive oxidation, because we don't want to go for the combustion process where we get the CO2 and H2O. So in passive oxidation we get CO plus H2. So that's why we supplied passive oxidation process, which biomass is applied with less than the stoichiometric amount of oxygen needed to the complete combustion, so around 25 to 40%. When the oxygen is supplied by air, low energy gases are formed that contain higher concentration of hydrogen, carbon monoxide and carbon dioxide than medium energy gases. When pure oxygen and oxygen enriched air is used, gases with higher energy values can be obtained. These are some information. In some partial oxidation process, the various chemical reactions may occur simultaneously. Any kind of combustion reaction or partial oxidation gasification reaction, hundreds and thousands of reactions, not thousands, though, then also hundreds of reactions occur in simultaneously, because there are so many different amount of product is there in our reactants are there in our biomass. It got reacted with each other in the presence of some catalyst or with and without a catalyst, and you will get some reactions, continuously reactions are going on. In others, the reactor may be divided into zone. So reactors, whatever the reactor which we are using in the gasification, can be divided into zone. One is the combustion zone, that supplies the heat to the promote pyrolysis. So pyrolysis requires some higher temperature. So how can we get higher temperature? In the first phase, combustion reaction is taking place. So combustion reaction is will get the oxygen of stoichiometric amount and get converted into CO2, and that will increase the temperature, and that temperature will be useful in the pyrolysis in second zone, and the third zone, which is a drying, or the overall result of which is a partial oxidation. So final product drying. This is not a before drying. And this is a gasification, but maybe you can't properly see. I have another figures from the internet. So this is a dry gas. It is going to the combustion process, then pyrolysis process, then drying process. And here you will get the common and whatever the slug which we are getting is a biochar or char S or something. We can it and finally using some product, whatever gas which we are getting, it will go into the scrubbing unit, where you are getting some unwanted gas which can be recycled back. Whatever the final desired gas is there, you will convert into the drying and all, and then we get the final product gas, which is a CO plus H2 or COH2, which is a producer gas. And whatever unwanted material is there, it can go separate in the separation in the solid, liquid, or any kind of vapor material gas is there, go for the separation, and you will get different product out of it also. But dried feed has some dried product is converted into some chemicals, chemical product. Okay, so the here it is already mentioned the same thing, gas temperature from about 315 to okay. So we'll see. So this first we understand the gasifiers, gasification and things. Now depending on to the design of your gasifier, there are many different kind of biomass gasifiers are there, depending on your final process and depending on to the desired product, as well as process which you want to follow. So major is if you can't see able to see here. So mainly if you just talk about, then the fluidized bed is there, and another, if you in the easy word, the one is a fluidized bed kind of gasifier, another is a fixed bed kind of gasifier. In the fixed bed there are two different sections: updraft gasifier and downdraft gasifier. So this updraft, in what is happening in the updraft, fuel enters from the top. So whatever the fuel which you are using, it enters from the top, and gasifying agent from the bottom. Okay, so whatever you are using the gasifier agent biomass, it will come into the bottom. So means fuel in the sense this is a biomass, and this gasifying agent, which is the for the gasification, steam, air, whatever you are using, which will come from the bound. Or downdraft, when both fuel and gasifying agent enter from the top. So fuel as well as air, actually it is from here also, and it is somewhat like from in middle also. It depends on to the which is the section. So first you can see this is a drying section and pyrolysis section, and this is a reduction oxidation section where reaction is taking place. So exit that point you will get this gasification agent which gasify your biomass. So your biomass is always on the top. Or biomass or fuel, you can convert it, you can consider fuel. So but in the updraft you will get the air or gasifying agent from the down, and in this it is in the middle. So in the updraft gasification, the char at the bottom of the bed meets the gasifying agent first, complete combustion occurs, producing H2 and CO2 and raising the temperature to 1000 degrees. So obviously it is meeting in the updraft gasification, it only here only it can meet, and the temperature is increased. So these are the packed bed kind of two different configuration, updraft gasifier and downdraft gasifier. Other than that also there are many different kind of gasifiers, but if you just go to few different two different then this fixed bed, then one is a circulating fluidized bed. So here we have fuel and air here only. So we are providing the air, then it is a fluidization process is take place. So solid is converted to gas, and gas will be coming out, and if your still solid is there, it will be again recovered and put it back, and this is like circulation of the fluidizing bed is taking place. And another is an entrained flow gasifier. So whatever the fuel and oxygen and all these things you are putting for here, you are providing the high temperature here, and then in between some entrainment is there. Entrainment is there in the form of some packing or in the form of some baffle and mechanical arrangement or configuration. So you will get your product got gas got separated here, and your whatever the unnecessary products leg is there, it will be separated out in the another direction. So this is how these gasifiers are there. And some more gasification, if you want to see that biomass gasifier design. This is a bubbling fluidized bed. It is a fluidized bed. We just see that is the same one. And this is a circulating fluidized bed or the bubbling fluidized bed. Here our biomass is come into from here, and we provide the air from here, and the fluidization is take place. And from this cyclone separator is there. Cyclone separator used for the separate out the gas from the solid. Whatever gas you are getting, it is a final product gas, and solid will be again recycled back. So the biomass is fed from the side and below the bottom or below the bottom of the bed, and the gasifying agent's velocity is controlled so that it is just greater than the minimum fluidization velocity. So what is the minimum fluidization velocity? Minimum fluidization velocity, if you just visited in the mechanical unit operation, so minimum amount of velocity is required of it is air to just start to fluidize the bed. So it just small, if you consider it 5 meter per second velocity is required for the air for the which is a minimum fluidization velocity. So 5.2 or 5.4 must be maintained, which is just greater than the minimum fluidization velocity. So there will be no very rigorous fluidization is taking place. The product gas exists from the top of the gasifier, and S will be in the down. These are the another is a circulating fluidized bed. We just see here this is a bubbling fluidized bed. Okay. So the velocity is not that much high. But if we talk about the circulating fluidized bed, two integrated units. It has two integrated units. In the first unit, the bed material is kept fluidized by the gasifying vessel with a high velocity than that found in a bubbling fluidized bed. So here, maybe you can't see properly. So, but if you just consider this one, it's like the bubbling fluidized bed. Anyway. This is a circulating fluidized bed. So this can be the answer. Here we are providing very high velocity. So the whole bed is in the circulation mode. It will go into this one, cyclone separator. So and this allows the bed material to be fluidized to a greater extent into the bubbling fluidized bed. The overall resistance time is higher. So here the whole particle gas is again recycled back and back, because solid particle go into the another section is coming back, so resistance time will be higher and effectiveness will be the higher. But the main thing is in a product gas you have to put some entrainment bed material that which can separate the product gas from the bed. So like here in this cyclone separator, you have to provide not only simple cyclone separator, or you have to put something where your final solid product will not go with the gas. While this bubbling fluidized bed, we are not providing too much velocity, the bed is always remain here. If our product is there, then we can recycle it very less. Then another process is a supercritical water gasification, or it is also known as a supercritical water oxidation of waste material. Maybe you can't see properly. So, but the important parameter from the professor side, this is a SCW reactor. You can get the flue gas and classification gas from there, and product is also coming out of that. So product gas is again CO plus H2O. Again another gas is as a supercritical water. So first of all, to understand what is a supercritical. So supercritical is the state where your compound or your material is not present into the liquid state or into the vapor state. It is in the particular state which has higher temperature and higher pressure than the supercritical temperature and pressure. So it can convert it into the supercritical state. So it has the characteristics of both liquid also as well as vapor also. So if you have the supercritical water, then it has the characteristics of the liquid and vapor both. So even liquid biomass such as the olive mill water can be utilized. Many kind of biomass we can use, because generally the solid biomass we can go for the biomass gasification process. But here our water is in the supercritical condition, so still it has a liquid characteristics also. So if you have liquid biomass, we can also use it. If you have solid biomass, that we can also use it. Tar and cork formation are created by the rapid dissolution of product, because of finer product got dissoluted into the supercritical water, and that water we can separate out, and we can separate it out the final product out of it, and whatever in the normal condition which we get. So why it is important? Although it has economically it has much more challenging, but the priority of the product or the efficiency of the product is very high. It is a high gasification efficiency, low tar formation, and these two are the main benefits. So if you guys see that this graph is not that much visible, but yeah, if you go for the more than 600 degrees centigrade for the supercritical water gasification, hydrogen production is increased, carbon monoxide is increased up to 500 to 660 degrees centigrade, then decreases, methane is got decreases. So this will be helpful in finalize our product into the maximum fraction of the H2 CO we will get if we are using a supercritical water gasifications. That's why people are using this technology. The limitations and all: high pressure requirement, high temperature resistance, just materials we need to take care of, high energy requirements are there. So you can see here the sludge flow is there. This is a feed tank, and this is a supercritical water reactor. So whatever the feed tank is coming, this is a preheater. So whatever the heat already heated from after the reaction, we have this high temperature steam, high temperature water, supercritical water and product mixture we can use into the as a heating medium for the preheating our material, and then we have the small furnace also for preheating, and then we can feed into the supercritical water reactor. And then we are providing the liquid oxygen in the limited amount, because here we are providing the liquid oxygens. So this will be very much easily react with the H2O supercritical water, and we will get your products out of it. So whatever the product is getting, you can feed into directly into the power generation, because you have the high temperature steam you can use for the turbine, and you will get the power, as well as the condensation you will get the water, which water you can use it for the once this heat you can utilize for the power consumption. Other than this heat again you can utilize, and you can remove the CO2, oxygen, nitrogen out of it, and means this is a supercritical water condition with for product C1H2. So if you reduce the temperature, you will get the water. You will reduce whatever the gas is there present in the gas, you can remove it out from the separator, and finally you will get some products which you can use for the transpiration, or another is the water. This water you can again convert into supercritical form, and you can use it here. This is a simple or you can see maybe advanced than the professor's proceed, where this is a reactor and that product is coming, and this is going to phase separator. You will get a product, you will get a clean water, and again recycle. But this is actual people are working on this kind of interconnected and in process, where you can not only conserve the energy, but you can utilize the energy, you can produce the energy. So another is a pyrolysis. So pyrolysis is the direct thermal decomposition of the organic component in the absence of oxygen. In that, oxygen is not provided. So thermal decomposition of organic compound into the mainly most of the time in the charcoal. So but it has a yield it has a many different kind of useful products, not only charcoal, liquid and solid derivatives. Eventually pyrolysis processes were utilized for the commercial production of the wide range of fuels, solvents, chemicals. So this is mainly used for the different products, chemical production also. So here if you want to go for understanding the pyrolysis, then you have to understand which different kind of type of the biomass composition, what is the reaction temperature, pressure, what is the time, many things are there, what is the catalyst you are using. So this will be helpful to finalize your process. The accumulation of considerable experiment data on this parameter has resulted in advanced pyrolysis process. So there are some advanced pyrolysis process where you converted biomass into the liquid fuel and as well as various chemicals in very higher yields. So pyrolysis is a modern technology. It is a very modern technology used for the maximum possible energy. You can extract the maximum possible energy from the biomass using the combustion process, gasification process, and pyrolysis process. These three processes are combined together with pyrolysis process also taking place. So you can consider this pyrolysis. This our feedstocks is there. It has lignocellulosic feedstock, which has cellulose, hemicellulose, and lignin. You go for the pyrolysis, you will get the products, which is a bio oil, biochar, gas, which are direct products of the pyrolysis. You can upgrade this product and use in the refinery. You will get final biofuels and biochemicals. And other than that, by using this pyrolysis, you will get this coal and all. You can again use this another sludge and another waste material. You can do the co-pyrolysis, and you can go for the catalytic copolymers. Catalytic pyrolysis, in the presence of catalyst, you will get the catalytic hydropyrolysis. Means these all come into the will give you some different kind of products. If you provide the heating in this pyrolysis, so there are two different methods. So solar pyrolysis is also there. If you just, these are the not actually the whole one process, but this can be pyrolysis technologies, which are the different technologies. Co-pyrolysis, catalytic pyrolysis, we can use it in the presence of catalyst or in the presence of different materials. Pyrolysis present on the different two different kind of biomass. That is the co-pyrolysis. Feedstocks are this thing. Products are these different ways. And if you want to just understand how we can achieve the higher temperature, so one is you can go for the microwave. So then from the microwave, it's a microwave pyrolysis, and if you use a solar pyrolysis, which is much more renewable and futuristic option. So the questions comes many times from the types of the pyrolysis and how much residence times and products are there. So mainly pyrolysis technology processes are, one is a carbonization. It requires days to be completed, and in the heating rate is very low, temperature is around 400 degrees centigrade. You will get the products as a charcoal. Conventional pyrolysis, it requires 5 to 30 minute whole residence time. The heating rate is low, 600 degree temperature. You will get oil, gas, charcoal. Fast pyrolysis is the type of pyrolysis where this whole process is taking place in under 0.5 to 5 seconds. It is a high heating rate. So this is not the same table which is there in the professor slides. I use in some other table, but you can follow any kind of table. Just follow that table, but this will be give you some much more insights and much more different kind of process. That's why I put it here. So heating rate is very high, 650 degree temperature. Bio you will get flash liquid or flash gas. Not only flash pyrolysis, or not only one time. One time there is two different times: flash liquid pyrolysis, flash gas pyrolysis. Both have the less than 1 second residence time. The whole reaction is taking place with the our biomass will be residence time lower than the 1 second. Heating rate is too much higher. It is more than or near to around 650 degrees. Get bio. If you have flash gas, then chemical and gas. You have ultra flash, which requires residence time of 0.5 second, less than 0.5 second. Heating is too much high, around 1000 degrees centigrade. You will get chemical and gas. Vacuum pyrolysis 2 to 30 seconds. Medium heating rate around 400 degrees centigrade. Bio oil. Hydropyrolysis less than 10 seconds. High less than 5. Bio oil. Methanopyrolysis. Okay, so now in the pyrolysis like gasifier, we have different kind of pyrolysis reactors also. So fluidized bed reactor can be used as a pyrolysis process. So biomass is coming, this gas is coming, fluidized bed, going to cyclone separator, charcoal, you will get the charcoal, whatever gas is there, or bio oil is there, you can turn it to bio oil, whatever gas you can use, recirculate and again. Circulating fluidized bed, the same thing. Whatever the maybe it's used for the biomass which agriculture, which has the sand and charcoal. So whatever the product and gas is go into cyclone separator first. You will remove the sand, which will be not useful. You will again put it back, and you will go for a cyclone separator second, where you get charcoal. And other than that, you will condense the gas, volatile gas. It will convert into liquid bio oil, and another gas are there which you can circulate. Ablative plate reactor, where your biomass is coming into a rotating plate, where heating is provided. You will get the charcoal and another gas model. Screw reactor, where it comes into a screw, your biomass is coming into the form of soup. There are two heaters. You will get the charcoal as a solid product. In the liquid gaseous product, you will get gas, which in that you can remove the after condensation bio oil, and non-condensable gas you can remove it out. Rotating cone reactor, this is in the form of this rotation is taking place, and the charcoal is the final product is coming out like this. whatever the gas material is there, you can condense it out into the bio is a liquid, and gas are the non-condensable gas. And this is a vortex or cyclone. The same kind of things is there. It is going to cyclone and now only 3-4 slides are remaining, 2-3 slides, and then we will close this today's discussion. So rotating cone reactor, and as you can see, we just discussed this is rotating cone reactor, biomass and heat sand is coming. So important thing is, so rotating cone reactor requires the mixing of biomass and hot sand mechanically, and does not require the use of inert gas. Here we are mixing the biomass as well as hot sand, and the feed and the hot sand are fed into the bed. So hot sand will be supplied at high temperature at bottom of the cone, where this transferred to the lip of the cone during the spinning, and this hot sand we are spinning, so sand has a lower density, and so it can be equally distributed among the biomass, and the vapor generated is whatever vapor generated, it can get condensed. So we can focus on the vapors, and the char and the sand are composite with the sand being heated up again and reintroduced and remixed with the fresh feedstock. So these are the advantages and disadvantages of different kind of bed reactor. If you go for the fixed bed reactor, then it is a simple in design, reliable, biomass size independent, which any kind of size you can put it. It has disadvantage like high carbon conservation, high amount of carbon will be get. You will get in a product long solid residence time. Residence time is much more long, low as carry over, and difficult to remove char. If you talk about the bubbling or fluidized bed, the simple design and easy operation. Disadvantage is temperature control has some issue. You can't provide a good temperature control all over the process. Suitable for large scale operation application, small particle size are needed. Circulating fluidized bed, well understood technology, better thermal control, better than the temperature control than the bubbling fluidized bed. Larger particle size can be processed. And large scale, what are disadvantages? Large scale production difficulty. If you gone for large scale production, hydrodynamics will be complex. Charcoal is too finer, which has very restricted applications. Then rotating cone has a centrifugal force, circulates hot sand and biomass substrate, no carrier gas required. That's why we are not using any carrier gas. The sand is itself is useful for carrying out the whole temperature distribution, but it is a difficult operational process. Smaller particle size needed. Large scale application is difficult. We talk about the vacuum reactor. The oil is clean, can process large particles, no carrier gas is required, low temperature required, condensation of liquid product is easier. And the disadvantage is a very slow process, not very slow process. Solid residence time is too high, poor heat and mass transfer rate, more water will be generated. So these are be helpful for solving some assignment problem. So now we are focusing on the DBT2 technology. Then we will close our discussion. There are two different kind of technology, which there are some questions are there. There are many technologies are mentioned, but out of these two, one is developed in the India. So Department of Biotechnology and ICT Institute of Chemical Technology, 2G ethanol technology they developed. So it is a validated and demonstrated in the form of 10 ton per day at Kasipur, Uttarakhand, in the Indian glycometer. So this is a very well success story from the India itself, and it is a proud moment. And then we can in future will develop many more this kind of technology, which will be helpful to convert our biomass into the final biofuels. So this is a 2G ethanol which we can blend into the petrol and diesel for the in the particular amount, and that we can use it as a fuel. This technology plant designed feedstock flexible. Any kind of these are the much more good advantage that any kind of feedstock we can use from hardwood or cottonwood or small softwood. The technology employs continuous processing from biomass size reduction to fermentation, and converts biomass fat to the alcohol within 24 hours. Other technology take 3 to 5 days according to them, but this can be 24 hours. The plant design with a low footprint also, which has low carbon footprint, which is the low carbon generation, carbon emission, and which has a advanced reactor design. So first we have the lignocellulose biomass. First go for the pre-treatment, then saccharification, which we call remove the glucose, hemicellulose and cellulose, and then saccharification process. Oil you can generate it, alcohol you can generate it. Then alcohol is ethanol, 2G ethanol, you can separate it out, and then fermentation and purification of the sugar, which we go into final final alcohol product. So saccharification is just you will get the sugars, and sugar got separated out, and then by using the fermentation process you will get the alcohol. So good advantages, good better technological development. If you can understand what are the advantages in simple word, the fractionation to sugar and lignin, rapid, efficient process, required less than 24 hours, high conversion, enzyme chemicals are recycled, so you can recover and recycle back, zero waste, silica inorganics recovery. So this is the abscale process which we develop 1 kilogram per day 2009 to present, which is still working. The pilot say 1 ton per day, and the commercial stage is 10 ton per day, which we develop in the March 2016. The other is a BTG process. BTG process is the fast pyrolysis process developed from in the Netherlands by the University of Twente. So biomass particle at 2 temperature, hot sand particle are introduced near the bottom of the cone, where solids are the mixed and transported upward by the rotating of the cone. So this is the process. We are not going to the discussion. In this type of reactor, rapid heating, a short gas phase residence time can be realized. Okay, so this is the biomass is fed into this cone reactor, and this bottom cone is there. So sand is also fed into it, and whatever product which we get in the form of vapor, which we pour into the separator, and the solid product of sand and charcoal we recycle back to the again non separator, where we use the air in the as a heating medium, and then this can be converted into the flue gas. This product mixture is going to the cyclone separator, where you get unwanted as flue gas are there, and whatever the vapor you got here, this will like the cooling flash tower, where you reduce the temperature. So gas and liquid got separated. Like liquid is converted into liquid is actually oil. You can put it, you can store it, and whatever gas you will get, it will go into the flue gas, CO plus H2, and you can use it in the steam for a power generation. So this is all BTG process. So like with this we end to the today's discussion, and I attached the one quote from the Swami Vivekananda, that never say no, never say I cannot, for you are infinite. So you don't have to you don't have to be belittle or demotivate yourself by thinking you cannot do anything. You are infinite, all the power is within you, you can do anything. This is some motivational quotes, and this is my mail ID. You can take the note of it. If you have any question, you can put it in it, we can discuss not only the assignment question, but if you want to discuss anything more. So with this I am just stop. Stop sharing the things. Okay, so if you have any question, you can ask me, or else you can leave. All the discussion was take place. I will convert it into the recording and then upload it into the YouTube by tonight, and you will get the YouTube video link into the Excel sheet which is provided into the course in the course as I think resources. Okay, if you have any questions, then you can ask, or else I can stop close the meeting. Okay, yeah, I actually next time onwards I will go into the much more realistic things which will be helpful, and because in the professor lectures there are so much information, so that's why little bit difficult to understand what the things are actual importance of all these parameters things. So that's why we can go into the detail, and it will be helpful for everyone. So we are not here just for the assignment solving, but at least you can understand the funda behind the topic, and that will be helpful for you in your final exam. So you can leave the meeting. Okay, thanks. So I am closing the meeting now.